In this lecture, we want to talk about this concept of the law of uninhibited growth or decay. And this is an example of mathematical modeling. So here we want to model the size of a population. And so the main principle here is that the rate of growth of a population, growth or decay, right? The rate of growth of a population varies directly with its size. So for example, the more people, let's say we're talking about a population of human beings, the more people that you have in a population, the more people will be born or the more people will die. So the rate of change of a population is directly proportional to the size of a population at any time t. So the way we want to write that down, let's say P of t is the size of the population at any time t, then that means P prime of t is the rate of growth. And if it varies directly with the size, well, P of t is the size of the population. And to say that y varies directly as x is the same thing as saying y is equal to k times x for some constant k. So to say that the rate of growth varies directly with the size of the population means that P prime of t is equal to some constant k times P of t. So we'll call k the growth constant or decay constant. So if k is greater than 0, then we'll say that k is a growth constant. And if k is less than 0, we'll call it a decay constant. So at any rate, these things, this constant k, we will assume that it is constant. So when we say a population grows at a constant rate, right, we're referring to the constant k here. All right, let's go ahead and try to find an explicit formula for a population that obeys this law of uninhibited growth. So again, P is a population. It varies directly with its rate of change, or the rate of change varies directly with the size of the population. If this is true, then the size of the population at any time t is given by this exponential expression, P0 e to the kt. P0 is the initial population, so P of 0, if you like. And then k is that growth or decay constant. So P of t varies directly. That means P prime is equal to some constant k times P. So how do we derive this mathematical model for the size of a population? So we'll start here with the original expression. The rate of change of the population varies directly with the size of the population at any time t. So P prime of t is equal to k times P of t. I can go ahead and divide both sides by P of t. We'll certainly assume that the size of the population is not 0. And so now that means that P prime of t over P of t is equal to k. So in order to solve for P of t, we need to get rid of the P prime. This is called a differential equation. So we'll go ahead and look at the antiderivative of both sides. So the antiderivative of P prime over t is equal to the antiderivative of the constant k. And this antiderivative is with respect to the variable t. So now, what is a function whose derivative is P prime over p? Well, certainly the natural log function has that property. The derivative of this thing, remember, it's take the derivative of the thing in the parentheses and put it over the thing in the parentheses. So the antiderivative of P prime over p is just the natural log of P of t. The antiderivative of any constant k means you just tack on the variable. So this is k times t plus some constant of integration c. So now, how do we solve for P of t? So the way you get rid of the natural log is to exponentiate both sides. So you slap a giant E underneath both sides, and that will get rid of the natural log. So now P of t is equal to E raised to the kt plus c. But now e to the kt plus c is the same thing as e to the kt times e to the c. And I'm just going to go ahead and call this thing e to the c. It's a constant because c is a constant. So I'm just going to call this whole thing c. So that's what we mean by absorbing constants as much as possible. I'm just going to give this thing the name c. So now, what is c with respect to the rest of this system? Well, if I plug 0 in for t, that's the same thing as c e to the 0. Well, c e to the 0, remember e to the 0 is just 1, so p of 0 is just c. So instead of writing p of 0, we just call this p sub 0. So now p of t is equal to p sub 0 e to the kt. So here's the good mathematical model for studying populations that grow or decay at a constant rate. All right, here's an example looking at the law of uninhibited growth. So we've got, in a lab, I guess, we've got a single cell of E. coli will divide into 2 cells every 20 minutes. So we want to assume that at the beginning of our experiment there are 60 E. coli cells present. So we want to do these 6 things. First, find the relative growth rate. So that's find the growth constant K. Second, we want to find an expression for P of T. We already know most of it. We just need to fill in a couple of the variables, I guess. And then third, we want to find the size of the population after 8 hours. We want to find the rate of change of the population after 8 hours. And then we want to find the size of the we want to know when the size of the population will reach 20,000. So if we start with 60, we know that it's going to take 1/3 of an hour, so 1/3 of an hour to go from 60 to 120. So 120 is equal to 60 e to the k times 1/3. We just need to solve for k. So divide both sides by 60, you get a 2 on the left-hand side. To get rid of the e, we will natural log both sides. So natural log of 2 is equal to k over 3. Multiply by 3, get out a calculator, punch it up, you see that the growth constant is 2.07944. So now you can take this thing in item 2, we wanted to find an expression for how many cells will we have after t hours. Well, we've got everything we need. We've got the initial amount and we've got the growth constant k. So here's the model. How many cells will be present after 8 hours? Just plug 8 into this thing, everywhere you see a T, punch it up on a calculator, and you get 1.007 billion after 8 hours, right? So we started with 60, and then we explode up to 1.007 billion after 8 hours. So the rate of change of the population, the rate of growth of the population, I know that sounds roughly the same as relative growth rate. Remember, p prime of 8 is equal to k times p of 8. We know what k is. We got that in part 1. We know what p of 8 is. We got that in part 3. So you just need to multiply those things together, and then you get roughly 2.1 billion people every hour. The instant at 8 hours, right? So at 8 hours, we can roughly assume that after 9 hours, we will add another 2.1 billion. So roughly after 9 hours, we might be closer to 3 billion. And then when will the population reach 20,000? So solve for t, right? Any question that asks when, you want to solve for time. So when will the population be 20,000? So we write 20,000 is equal to 60 e to the k times t. We just need to solve for t. So divide both sides by 60, you get 333 1/3 is equal to e to the kt. Now we're trying to solve for t, so we need to get rid of the e, so I'm going to natural log both sides. That means that so the natural log of this thing, 5.809, is equal to the natural log of the right. We'll just cancel the e out. So 5.809 is equal to 2.07944 T. Divide both sides by 2 and change, and you get that T is equal to 2.8 hours. So in the first roughly 3 hours, the population only grew to 20,000. But in the last 5 hours, it blew up to 1.007 billion. So you can see this thing is called exponential growth because the population grows exponentially, right? So the initial few hours, it won't grow that much. But then as soon as you hit what some people might call a critical point, then this thing shoots off to infinity very quickly. So just to give you some idea of how populations of organisms or people or whatever will grow if the growth is uninhibited. Okay, here's another example of exponential growth and decay. So the last example we saw was exponential growth because we had a positive growth constant. Here we're going to look at exponential decay. So we've got some radioactive material, radium-226, and the half-life of a substance is the amount of time that it takes to go from its original amount to half of its original amount. And so we're saying here that the half-life of radium-226 is 1,590 years. So that's how long it takes to go from, let's say, 100 milligrams of the substance down to 50 milligrams. So we want to find a formula for the mass after T years. So we want to find that exponential model that we've been studying. And then we want to find the mass of the radium after 1,000 years. And then finally we want to ask, when will the mass of the radium be 30 milligrams? Alright, so the first thing we want to do is find the usual model for exponential growth or decay. So I forgot to mention in the previous slide that in the problem we will assume that the initial mass of this radium is 100 kilograms. So they tell us what the half-life is. And you really don't need the initial amount in order to find the half-life. What that means is it takes how long to go from the original amount to 1/2 the original amount. So in this case, we know that it takes 1,590 years to go from its original amount to half the original amount. So as always, step number 1 is to solve for K. That's okay because the P zeros will cancel, right? So it doesn't matter what P zero is, it's going to cancel anyway. So now we've got 1/2 is equal to e to the 1590k. So how do you solve for k? Well, natural log both sides, that'll get rid of the e. So now you've got natural log of 1/2 is equal to 1590k. And remember, natural log of 1/2 is the same thing as natural log 2 to the negative 1, which is negative natural log of 2. So natural log of 1/2 divided by 1590 is really negative natural log of 2 divided by 1590. So we do get a decay constant, right? This is a negative number, and so we should expect exponential decay. So now that we know what k is, and we know what the initial amount is, we get our model, right? So this is the model that tells us how much radium we have after t many years, and that amount is given in kilograms. So how much radium do we have after 1,000 years? Well, just plug 1,000 into this thing, work it out on a calculator, and you get roughly 65 milligrams. All right, so we go from an original amount of 100, and it takes 1,000 years to decay down to 65, right? So we don't really lose that much after so much time. And then how long will it take for this mass to decay down to 30 milligrams? Well, we want to know when the amount will go from 100 down to 30. So remember, the when questions, we want to solve for t. So 30 is equal to 100 e to the negative natural log 2 over 1590 times t. So I'll start by dividing by 100, so 3/10 is equal to e to the negative natural log 2 over 1590t. I will natural log both sides, so now I get natural log of 3/10 is equal to negative natural log of 2 over 1590t, and so now I just need to solve for t and punch it up in a calculator, and you get 2,762 years.